Great, so I'm going to tell you about Cedar. It's a language we've been developing for the last 2+ years at AWS. And by we, I mean myself and a pretty large team. You've probably been looking at the author list up there. You might recognize Amina Torlock, who was, like me, a former professor. She was at University of Washington, but now also has joined AWS as part of this team. So the context is the question, what is authorization and why do we need a language for it? Well, pretty much any kind of application that you might imagine yourself writing probably has need of a permission system. You probably have multiple users. Those users can perform different activities. And you need to define, well, who is allowed to do what? Now, there's lots of theory for access control and authorization. You've probably heard of role-based or attribute-based, maybe even relation-based access control. There's conferences about it. So the idea of how you might structure your permission system in your policies is well understood, but that doesn't necessarily translate to easy to implement. So to illustrate that, let's consider a simple application, Tiny To Do, where multiple users and teams can create and manage to-do lists. Here's a bit of code for Tiny To Do, the handler for the get list action that a user can call to find out what to-do lists they're allowed to look at. Now, most of the logic that you see inside of this action in the beginning is determining whether or not this particular user is allowed to perform this action or not. It's saying that, well, if the user is an administrator, or they're the owner of the list, or they're one of the readers of the list, or they're one of the editors of the list, then they're allowed to have access. Now the code is actually framed in the opposite way. If you're not one of those things, then I'll just return. And if you are one of those things, the control flow will carry on and will actually retrieve the contents of the list. So you can think of reasons why this might be hard to, and this is the background, why this code might be hard to author, audit, and maintain. You have to actually write all that correctly and do the inversion of the control flow. If you're somebody who didn't write the code, you need to go look at all of the code and all of those different handlers to make sure that all of it together makes sense. And then finally, for maintenance, if ever you decide to change your permission system, you need to go into the code for your application and make edits to all of that code. And maybe you're going to have to make edits to the same kind of code in different places. For example, that first line there that says you're an administrator, that line is just duplicated across all of the different handlers. You have to fix it in every place. Right, so that's maybe not so great. So an alternative is to delegate your authorization logic to a separate authorization engine. And now you can see that the code is just going to ask, is this request authorized? If not, I'll return. If it is, then carry on with the logic. How will that engine make the determination whether or not the request is authorized? Well, it will consult policies written in a domain-specific language that describe the permissions. So, in fact, the permissions I mentioned before are all captured in these 3 policies. They say that any owner is allowed to perform any action on a resource that they own. That's the first policy. The second policy says, that's just below that, administrators can perform any action. So a principal that's in the admin team can perform any action. And then the last one says that, well, you're allowed to look at the contents of a list if you're one of the readers or the editors. Okay, so all of these things together capture that logic that we saw embedded in Python code before. But actually, you can see that a bunch of these policies, the first 2, capture actions beyond just get list. They capture any action. You can perform any action that you're for a list that you're an owner of. And if you're an administrator, you can just perform any action at all. So I'm not having to duplicate that. Because all these policies are in one place, it's easier to look at them and understand them. I don't have to read all of my application code to figure that out. And likewise, it's easier to maintain. I can actually change my policies without changing my code, allowing my application and authorization logic to evolve somewhat independently. Okay, so that's a better situation. Now, Cedar is a new authorization language. This idea of separating authorization logic into its own language is not a new idea. There exist other languages, but Cedar is new. And I'm going to tell you why we built it in a minute, the properties that it has that other languages don't have. Right now, Cedar is open source. It open sourced back in May of 2023. And it's the core of a service, Amazon Verified Permissions, that will perform authorization on behalf of your applications. So there, that little call to is authorized. Using Amazon Verified Permissions, that will be an API call off to a cloud service that will consult policies in one place and give you an answer back, which gives you a bunch of benefits like having one console in which you can look at policies for many applications, logging, auditing, and so on, all in one place. Cedar is also used in another Amazon service for zero trust, and now there are a bunch of startup companies, in fact, that are starting to use open source Cedar to build things. Okay, so why do we build Cedar when languages for writing authorization already exist? Well, first of all, we wanted to build a language that had readable policies, ergonomic syntax and semantics, readable and easy to understand. Secondly, we wanted to build the language so that we could apply powerful static analysis tools to your policies. Instead of just reading your policies to understand them, we want to be able to apply SMT solvers, for example, or type systems to be able to validate that your policies make sense. And third, we wanted to build an authorization system that was fast and also safe. We wanted high confidence in the implementation of our language, and we wanted that language to nevertheless be fast so that people wouldn't feel uncomfortable about moving their authorization logic outside of their application code. In addition to these three things, or maybe to complement all of them, we built Cedar in an interesting way. We use a combination of formal methods and automated testing to convince ourselves that what we designed is actually what we implemented and deployed. Now, meeting all of these things is a balancing act. Being able to build an engine that's fast and safe, and one that you can reason about in a user-friendly way, usually is in conflict with something like expressiveness. You can imagine Turing completeness is probably not your friend if you want to have really good automated reasoning tools. And so I want to reduce the expressiveness of my language. I want to limit my authorization model to some degree so that I can gain some of these other benefits, but not so badly that users can't naturally express the policies that they want. So you're going to see how we try to maintain this balancing act as we move forward. Now, if I look at expressiveness, performance, and analyzability and safety as three axes, we can look at existing languages as tending to fall on two extremes. One is favoring expressiveness, so leaning more towards Turing completeness, but then maybe not being quite so performant, or at least not predictably so. And the other extreme being those being more performant. For example, think of simple access control lists or Unix-style permissions. Those things are going to be very performant to check, but they're not so expressive. They can't express role-based or attribute-based access control so easily, for example. None of the existing systems, to a satisfactory degree, supports analyzability and safety. And so Cedar is trying to find this balance between all three. All right, so then for the rest of the talk, I'm going to go through each of these three batteries included and explain how Cedar tries to meet the goals. So let's first look at Cedar in detail. So here's one of those policies I showed you before for Tiny To Do. And this policy says we're going to permit any principal to perform the get list action on any resource when that principal is a member of the readers group for that resource, or it's a member of the editors group. Now, if we look at the contents of this policy, the first part is called the effect. That's permit. The other sort of policy that Cedar supports is a forbid policy. We'll see those in a little bit. The second part is called the scope. So the scope always lists principal, action, resource in that order, and it optionally includes constraints on those things. So we can see here that principal and resource are not constrained in any way in the scope, so that means that any principal or resource is in play, whereas action is constrained to a particular action. And then finally, the conditions. This is a Boolean expression. It's either when, so it's the conditions conjoined with whatever the conditions are in the scope, or unless, so that's the negation of those conditions. And those are for Boolean expressions over other elements, the principal, action, and resource, that are going to come in as part of the request. Now, in terms of the data model, which is to say what can those expressions be over, Cedar has a generic entity hierarchy. So the principal, action, and resource are things called entities. We've seen the syntax for entities already. That's the type of the entity, colon, colon, followed by the identifier for the entity. So you can see action there as an entity. But we also have administrators and temps and interns. These are all user entities in our tiny to-do system. Entities can also have attributes. So attributes can be used for attribute-based access control policies. You can see, for example, the readers and editors attributes there that are part of the list. And we can see those down here in the bottom. The owner that we saw before, one of those other policies, along with editors and readers. So the semantics of a Cedar request. A Cedar request has 4 elements. It has a principal, action, resource, and a context. So for example, a request might come in that asks, is Kesha allowed to get list on list 1, 2, 3 with an empty context record? I'll talk about context records in just a minute. Now, Cedar's authorization engine is going to look at the policy to decide whether or not that request is okay. A request is okay if there exists at least one permit policy that is satisfied and no forbid policies. So Cedar is a default deny language. If no permits exist to authorize, it's going to be denied. If there do exist permits that authorize, those could be overridden by any forbid policies that are there. So you can think of forbid policies as like guardrails that prevent certain unsafe forms of permit policies. Okay, so let's looking at this particular request. We can see that it is authorized by that one policy, and that's because Kesha is in the readers group. Why do we know that? Well, the readers group for this list, 1, 2, 3, includes temp. And if I look in the hierarchy over here, we can see Kesha is a member of temp in the hierarchy. So Kesha is a member of resource, that is to say, list 1, 2, 3's readers group. Now, if Emma tried to get access, we would see that this access is denied, and that's because this particular policy won't apply. Emma is not a member of the readers or editors group for list 1, 2, 3. Just to show that when we have 2 policies, as long as any policy applies, access will be granted. So once again, that doesn't change anything for Kesha, still authorized by the first policy. But now Emma is authorized by the second policy because Emma is a member of the admin team. So with this basic setup, we can encode role-based, attribute-based, and relation-based access control. So for example, if I look at that second policy that we were just looking at, we can see that this is implementing a kind of role-based access control. That is to say, the principal is a member of the role administrator, and that is going to grant them the ability to perform any action for tiny to do. The entity hierarchy for roles is a hierarchy, so the in relation there is transitive. In our implementation, we implement these in checks by pre-computing the transitive closure for the entity hierarchy. So these checks become O of 1. The assumption here is that that hierarchy is not going to change so frequently as compared to the frequency of requests. And so pre-computing the transitive closure makes more sense than computing reachability for each request. Okay, then turning to ABAC, you can see that one of those policies, similar to the one we saw before, we show here at the bottom, there is a attribute owner, and this policy grants access to administrators as long as the owner, unless the owner of whatever it is they're accessing is a member of the VP team. So owner here is an attribute, and we're using the attribute in combination with the entity hierarchy to make our authorization decision. Attributes, as you can see here, are using the sort of standard data types that you might expect: Boolean strings, sets, records, things like that. And the when clauses and unless clauses can have expressions that are loop-free. So that's that nod toward reducing expressiveness to aid analyzability, but still fairly powerful with set membership, conditionals, string matching, things like that. Okay, and then finally, this idea of relation-based access control. You can think of readers as like a relation between one or more, or zero or more, I should say, users and a particular resource. And so this combination of attributes along with the entity hierarchy allows us to encode a notion of relation. So this policy that we've already seen is looking at members of the readers or editors relations. Okay, so stepping back, that's what we can do. Why did we set it up that way? We can see that policies basically have these two parts, the scope and effect, as well as the condition. And you might ask yourself, why did we set it up that way? We could have just had a large Boolean expression after the effect with just permit or forbid and then that expression. The reason is that we felt like this separation of scope and condition adds a bit more to readability. You can sort of read the policy as you walk down it. Principals who are a member of this team can perform this action on this resource, unless it feels more readable than just this Boolean expression here. But there's an additional reason, and that's for policy indexing. You might have many, many policies, and you don't want to evaluate every single one of those policies necessarily on every access request. And so you would like a quick way to find the relevant policies to your particular request. So that's what indexing is for. And that process of finding those policies we call slicing. So the basic idea for slicing is that we will use the constraints on the scope, the principal and resource parts, to create an index with which we store those policies. And then what we'll do is we'll compute keys for a particular request. And then, oops, that's not how that was supposed to happen. It's like perhaps I deleted the wrong slide. So what we'll do is we'll then look at a particular request. For example, Aaron wanting to get owned lists for Tiny To Do. And we can recognize that only the latter two policies can apply. And that's because Aaron is a member of the interns and temp teams, and not by any possibility a member of the admin team, whereas that first policy could only fire for members of the admin team. By indexing based on those scope constraints, we can very quickly compute keys for this request, look up the policies in the according to the scope constraints, and then remove a whole bunch of policies from consideration. So I'll show you some performance numbers at the end. But doing this approach gives us like a 10x performance improvement by being able to index this way. Okay, so that's Cedar's semantics and its basic policy structure. Let's now talk about static analysis tools for reasoning about particular policies. So here's one of our policies again. You can imagine making mistakes when you write your policies. For example, what if I made a typo when I typed in resource.readers and I was two E's instead of EA? Or what if I mistyped an action? I would like to get some assurance that I didn't make that mistake, because as a default deny language, that mistake might cause an access request to be rejected when it shouldn't have been. So to address that problem, we give users a way to write schemas that describe the expected type structure of the different entity types, as well as what actions are allowed and what principal and resource types we expect to accompany those actions in requests. We can then use that information to basically type check policies to make sure that they are consistent with those definitions. So for example, if I look at the action here in this particular policy, and I look at the definition here at the bottom for actions, I can see that this action does exist, get list, so that's not a typo. And moreover, that the principal and resource types that I expect are user and list, respectively. I can use that then to type check uses of principal and resource variables inside the policy. So for example, I can see here that principal in resource.readers, resource I know is a list, and lists as an entity have readers and editors, which are teams. So that's good, those attributes exist. I know because they're teams, they can be members of the hierarchy. So using the in functionality on them with them on the right-hand side also makes sense. I know that the principal on the left-hand side is also an entity, it's a user, and so it makes sense. And moreover, if I look at the definition of entity and team there at the top, this user in is saying what other entities in the hierarchy it can be a member of. So I can type check that sure enough it is possible for principal to be in resource.readers or resource.editors because users are allowed to be in teams. Once I have all this written down, I can type check my policies. I can also make sure that my application's use, its encoding of entity data, conforms to this schema. And moreover, the requests that I get conform to the assumptions that are made in the schema, assuming I want to pay that little extra cost. And having done that, I can therefore have assured myself I have not made any mistakes about improper entity relationships or unrecognized attributes. And in fact, I can be happy that there's a theorem that we proved that if validation of your policy succeeds and you satisfy the assumptions that you've laid out in the schema, that you won't get any runtime errors. Okay, so this is a nice benefit for policy writers. It's just standard type soundness result. And for those of you who like type checking algorithms, there's not very much that's fancy that's going on here because Cedar is not very fancy. One thing that's a little bit fancy is that the ownership checks, sorry, not the ownership checks, the attribute checks that we performed. Remember that policy that said resource has owner and resource.owner in team VP. Owner in that case was an optional attribute. And so we do sort of capability-based type systems where we keep track of those has checks to know that in the continuation that you're able to dereference that attribute knowing that it has actually been checked according to the application, to the policy code. We also support a sort of path-sensitive type checking using a variation of union types, taking some inspiration from TypeScript. Okay, so the other aspect of static analysis that Cedar supports is automated analysis using encoding to SMT. So basically we want to ask universal questions about the semantics of policies. For example, can I prove that two different sets of policies, one being a refactor of the other, are actually equivalent, that they have exactly the same permissions in terms of which requests are allowed and denied? And the way that we do that is we symbolically compile Cedar policies to SMT-lib formulas, and we send them off to a stat solver to see whether or not the negation of those formulas is satisfiable. If it is not satisfiable, then that means it holds universally. One thing that we take as a tenet in the development of Cedar is that we want our encoding to be provably sound, complete, and decidable. So we needed to preclude a bunch of features that might get in the way of that goal. So far, we have managed to hold users at bay who would like to add general loops and full-fledged regular expression matching and things like this that would compromise our ability to provide this. And we have proofs, soundness, mechanized, and completeness on paper for these results. So just as a little example for why you might want to do this, here are two policies. The first policy says that anyone is allowed to create lists or figure out which lists they own. And now here's a forbid policy, but interns are not allowed to create a list. So this is one of these cases where forbid is going to override a permit. Now maybe you as the policy writer don't like that, and you'd rather just write a single permit policy that captures the same logic. So the question is, did I get that right? Carl says no. So Carl is correct. There's going to be a difference between these two. And in particular, the policies on the left say that interns are not allowed to create lists, but it doesn't say they're not allowed to get which lists they own. Whereas the policy on the right-hand side says, no, interns are not allowed to get which lists they own either. And so when we run it through the SMT encoding and we ask whether or not this property is satisfied that they're equivalent, it will come back with a counterexample in the form of this request saying how these two things could differ. That gives us an idea, oh, let's refactor it to be this way, and now I can prove that these things are actually the same. So we feel like in the long haul, this is, yes?
So that's actually not what I thought the problem was, and so I think I thought the problem was that not permitting is different from forbidding, since forbidding overrules permits. So guess I have that wrong?
No, you have that right. So here on the left-hand side, what this is saying is you are permitted to create a list and get own lists, and that you being any principal. But if you're an intern, you're not allowed to create a list. So you can think of this as creating a positive set of permission tuples, and then this as a negative set that is eating into the positive set. And when I went over to this side, the positive set is smaller. It is saying that you're permitted to do these things unless these conditions hold. And so it's sort of constructively defining what the allowed permissions are, and it has constructively defined fewer than would have been allowed on the left-hand side.
But on the right-hand side, I could add some other policy that lets interns create lists. And on the left-hand side, I can't do that. So it's
Yes,
not
that's
like
correct.
contextually equivalent.
That's right. It's not contextually equivalent. It's equivalent in the current moment, not against all other possible policy stores. That's a good point. Right, so this idea of being able to do policy analysis we feel like is a really powerful feature that users will want, especially auditors that care about compliance or privacy, and they'd like some real assurance that they haven't made a mistake, they can prove properties about their policies in some way. And I'll just add, this is a key feature in general of being able to pull your policies out separate from your application. If you tried to prove something about your policies embedded inside of your application code, you've made your job a lot harder. Okay, so yes?
So on that note, if you look into anything along the lines of like basic sanity checks that anybody would want, you haven't accidentally forbidden everybody or haven't accidentally committed everybody or some drastic swing between the two?
Yes, yes. So basic sanity checks through policy analysis are actually the first thing that we've been looking at because they're the easiest thing from a UI perspective to show to customers. So vacuity checking, it's actually not hard to sort of misunderstand the use of negation and create a policy that just never applies. So we can flag that. It's also not so hard to do the opposite, where you make a policy that applies all the time, which would also be terrible. So that's sort of the first low-level analysis we expect to deploy, but then these other more interesting ones will follow. Oh, sorry, went too fast there. Okay, so the last thing is a fast and safe evaluation engine. So what do I mean by that? So the idea, again, recapping what Cedar is going to do for me in my tiny to-do application is I'm going to take my request that I got into my application code, and I'm going to package it up along with entity data that reflects the information needed for my application to decide the request. I'm going to send it over to the Cedar authorization engine, and it's going to tell me allow or deny with some diagnostics. Now, this involves an authorizer and an evaluator. The evaluator is the part that looks at each individual policy to determine if it's satisfied, and the authorizer is the thing that combines the results from evaluating multiple policies. All of this is implemented in Rust. So we chose Rust because Rust is fast. It interfaces nicely with other languages because it doesn't require a garbage collector, and also it's safe. It has a nice type safety guarantee. What we find is that for some typical applications, which I'll show you in a minute, about 10 milliseconds for a typical input. In fact, why don't I show you those applications now? Comparing Cedar to two alternatives. One is called Open Policy Agent. The language is called Rego. This has been around since maybe 2016. It's pretty popular in Kubernetes. So when we talk to customers, they often ask us, what about Rego? Should I consider using Rego? I'll tell you more about the pros and cons of Rego a little bit later. But for now, you can understand it as being based largely on data log. So it's more powerful than Cedar in terms of expressiveness, but its performance is a little bit less predictable now. It's implemented in Go. So this is a Rego policy for tiny to do. It's basically implementing that one policy that I wrote about being a member of the readers group. The first part says that I'm going to define a predicate allow read. Allow read is true if either any of those things in curly braces afterwards is holds. So using data log is goal-directed search. It's actually going to start at the bottom and say, in general, my authorization request is allowed if one of the actions, if I search through read actions, that's an array, that underscore there is saying there exists a variable such that. One of them is the input request action is one of the read actions, and I'm allowed to read. Well, how do I know if I'm allowed to read? Well, it's if one of those three sub-goals is holds. So allow write is going to be similar to the first two there for allow read. For allow read, it's basically going to look in an encoding of the Cedar entity hierarchy, but using Rego graphs to go off and see whether or not a reader is there or not. So we find informally that many customers don't like this syntax, and they find the goal-directed approach harder to understand than Cedar. You could argue that they figure it out, they would learn it, but this is sort of a first impression thing from them. The other thing I'm going to compare against is called OpenFGA. It's based on a system called Google Zanzibar, which you may have heard of. So Zanzibar is the authorization system that underpins Google Drive and Google Docs and that sort of thing with individual users, folder-based permissions, things like that. It uses what's called relation-based access control only, so it doesn't support attribute-based access control in the style of Cedar, but it's much easier to express what relations look like. So for example, this is sort of the expression of our reader-oriented policy from Cedar in Zanzibar. So it's a bit more uniform in its syntax. Easier to read, I think, than the Rego stuff is. All right, so let's compare those two things against Cedar for the tiny to-do application, as well as encodings of GitHub and Google Drive permissions, which we borrowed from OpenFGA and then ported over to Rego and to Cedar. So for these particular applications, basically Cedar is quite a bit faster. So basically the Cedar line is the green line that's hugging the x-axis. You can't see it at all. Whereas for the other cases, they're basically scaling linearly or a little bit worse than linearly. The difference between the dotted lines and the straight lines is the straight lines are medians and the dotted lines are the 99th percentile case. The x-axis is growing the numbers of users, groups, documents, and folders. The y-axis is time for a bunch of different experiments. We also just test out policy slicing. So for these particular applications, there's not very many policies in Cedar. I think there's maybe 4 or 5 policies. No, that's not true. Maybe 10 policies total for all the applications. This is kind of the benefit of both role-based and attribute-based access control. You can define one policy that applies to a large number of users and requests according to these predicates. But you can also basically just inline a bunch of that stuff. So instead of saying, oh, this person is a member of the readers group, every time in your application you add someone to the readers group, you could just plop in a new policy that allows that particular person to have access to these particular things. So that would grow the number of policies. But it turns out that this is okay if you do this in Cedar, if you take this style, because the policy slicing approach will very quickly decide which policies don't apply to you and improve your performance again. So in the worst case, if you didn't do policy slicing, Cedar would scale up in that way, which maybe we wouldn't like. But when we use policy slicing, the performance is much better. Okay, so back to fast and safe engine with Rust. That was the fast part. Rust is part of the story for safety, but it's not the entire story. We also, to convince ourselves that Cedar has been implemented correctly, build a formal model in Cedar, and we use differential random testing to make sure that our Rust code always matches the behavior of the formal model. So basically, we just generate a bunch of random requests, entity data, and policies. And then we feed them to both the reference and the production code, and we make sure that they don't differ. And if they do differ, then we found a bug. But we also generate proofs. So instead of just building that reference implementation in a simple functional programming language, we use a verification-aware language so that we can write theorems and prove properties about the language. For example, we could prove the default deny property that I mentioned actually holds. It's not just an intention, it's the truth. We could prove that our slicing algorithm that selects policies that are relevant is actually sound. It's not forgetting policies that it shouldn't. We could prove that our validator is actually sound, backing up the claim that I made before. Okay, and then we have mechanized proofs for those things. That would be great. And by differentially testing against that model, we can be even more convinced that our production code also enjoys those properties. So using this approach, we found 4 bugs due to failed proof attempts. They were all in the validator, unsoundnesses that we had missed. And we found, to date, 21 bugs using the differential tester. Some of these bugs are sort of outside the abstraction level of the model. So for example, we have an extension for IP addresses. We were using somebody else's Rust code for that, and we actually found a bug in their Rust code for how they parse IPv6 addresses. Whereas like half of our model on the verification aware language was writing a parser for IP addresses. And it turned out that writing it in this case, I'll show you in a second, in Daphne, was more reliable than this person's Rust code. Okay, so as I just hinted at, our verification aware language was Daphne. Daphne is a big project that's under active development in AWS. And Daphne really showed its quality in low-code proofs for basic properties. So in fact, all of these properties here, default deny, overrides, allow, sound spacing, we basically had to do no extra work, and Daphne automatically found proofs for those things. So that was really great. However, Daphne is based on SMT solving for generating these proofs, and what we found was for meta-theory proofs, like the one for the validator soundness, and also for the SMT compiler soundness, it was brittle, which is to say that Daphne will not figure it out automatically for you, so you have to write a bunch of code to sort of help it figure it out, and that code is brittle with changes in the rest of the system. If you reorder some definitions, if you rename them, you upgrade to a new version of Daphne or a new version of the SMT solver, proofs that used to work don't work anymore. They start to time out, and so on. So this became frustrating enough that we decided for an intern project, hey, what if we rebuild our models in an interactive theorem prover, in particular lean, and see whether or not the situation could be better. It should eliminate this proof brittleness problem, but we'll lose some of those benefits of automated proof, and maybe it'll be really too hard to do the proofs, and we won't want to do that anymore. So let's see. So first, I want to show you that actually lean is quite readable. So that's the code for the authorizer. What that code says is, first of all, I'm going to compute all of the satisfied policies, satisfied forbid policies. Then I'm going to compute all the satisfied permit policies. And then I'm going to ask if the forbids are empty and the permits are not. Well, if that's true, that authorizes my request. There exists a permit and no forbids. Otherwise, it denies the request. So that logic is pretty evident there. Once you get used to the lean syntax, you can go read the model, and it's very concise and helpful for you figuring out what Cedar is actually doing. This is the proof of deny, overrides, allow. So most of it is just a statement of what that means. I'm not going to read it for you, but that's, I think, a little bit harder to read. And the proof is just a series of tactics at the bottom that show that it actually holds. So comparing the lean versus the Daphne, for all of our proofs, the lean confirming those proofs, checking that they're correct, takes 185 seconds, whereas for Daphne it takes 519 seconds. This should be no surprise because Daphne is going off and calling an SMT solver that's using lots of heuristics to try to figure things out. So this was a benefit that we expected. In terms of the models themselves, if we look at the bits at the top, the lean column is the lines of code, first of all, for the authorizer and the validator, so that's the second 2 rows there. If you compare those against the Daphne, you can see that the lean code is a fair bit shorter, and that's because expressing those things in lean in a purely functional style just turned out to be a much more concise and easy thing to do. We didn't have to write lots of requires and ensures, pre's and post conditions and whatnot. We could keep all of that stuff separate. On the other hand, for lean, there were some recursive data types that we could not encode directly, that we could encode directly in Daphne. So we had to sort of create those things ourselves and prove some theorems about it, so that added a little bit of extra overhead. We do not encode in either lean or Daphne the parser. That would have been a giant pain. So instead what we do is we just reuse the Rust parser and test that parser directly, so there's no theorems about that. On the far right, you can see the column there for the Rust code. The Rust code is substantially larger than both the Daphne and the Lean. And so this is showing the benefit of this approach, and we have a formal model that's smaller, hopefully easier to read and understand, compared to the Rust code, which has all this stuff for error handling and optimizations, you name it, tests. In fact, all the tests there at the bottom, sorry, the total there you can see for Rust adds up to much more than the 3 rows. That's all the extra stuff in Rust that's there for testing, integration tests, and everything else that we don't have in the regular models. Okay, and then finally at the bottom there is the lines of code in the proof. And you've probably been looking at that while I've been talking. You can see that Lean is larger than Daphne. Again, as expected, there's more stuff you have to do by hand. So Amina Torlock is the one who did most of those Lean proofs for us. She did a bunch of the Daphne proofs. We were worried about those proofs taking a long time, but the validator soundness proof, which was the most involved, took 18 person days. It's a little bit unfair because we already knew it was sound. We had already done the proof before, so you would expect it to go a little bit faster. But it wasn't as bad as we had feared. We thought that maybe it would take a little bit longer. And in terms of maintainability, we had this experience of using mathlib, which is Lean's enormous user-contributed library of theorems and whatnot. And that was making proof times be really slow. So we switched to STD, which is a much more lean version of the math library. And that was really easy to refactor. So that was reassuring. Okay, so I'm getting to the end. Thanks for your patience and attention. I'm going to throw out a few research questions about Cedar that maybe some folks here would be interested in. So the first question is, how do we integrate Cedar into our applications so that we can be convinced that our actual end-to-end semantic goals are being satisfied? Right? So I have pulled the policies out of their own file, but there is still an intention matching the semantics of the application and the semantics of the policies. Right? When I called from that getList handler code in my Python example, I need to remember to pass getList is the action that I'm interested in, and oh, this is the user that's making the request, and this is the actual list I'm making the request on. If I don't interface with the Cedar engine properly, I pass the wrong action name, the wrong user, or whatever, then obviously my end-to-end goals are not going to be satisfied. So how can we bring these two things together? Maybe taking advantage of simple code tracking, taint analysis style technologies, maybe dependent types, where the questions about the policies can be mostly kept independent in Cedar, but you can still track that the code calls the engine, calls it when it's supposed to, passes the right parameters, things like that. Another thing I haven't talked about is policy management. So if you're an application like TinyTo, you're actually adding users, lists, and so on the fly. You could imagine adding new application policies on the fly, because maybe one user delegates to another user the permission to share that list with a different user. So in that case, my current policy store, this is kind of Carl's question, is not fixed one time for all time. It might be that new policies can be added because of permissions that currently exist in the store. So I want to care not just about the current state of things, but all states that it could possibly be in when reasoning about my policies. How do I do that? That sounds like an interesting question. We have a type system. We have an automated reasoning system for translating to SMT, but there's lots of other approaches we could take that are trade-offs in various ways. The type system, it goes very well with the current SMT compiler, which forces the type system to be a little more limited than some of our users might like. So again, finding that nice balance would be great. On the automated testing side, what we have found is that input generation is a huge pain. Being able to generate useful inputs that manage to cover all of the application logic in a good way is a painstaking manual effort. So finding ways to automatically develop better input generators would be very much desired. And for that matter, measures of testing success. We have definitely found that code coverage is a weak measure. No one here should be surprised by that. We're all trained that that's the case. But then we go off and act like it's not the case anyway. Oh, we have 100% code coverage. It must be good. Wrong. Every bug we've ever found was in code that we previously covered with some test. So code coverage is clearly not enough. What could we do instead? There are code independent mechanisms we could use to assess input coverage. Mutation analysis, mutation testing, legacy bugs. There's lots of ideas we could consider there. Okay, so that brings me to the end. Cedar is a authorization policy language that we've been developing that is ergonomic and expressive, supports powerful static analysis tools, is fast and safe. It's developed in this interesting formal methods plus testing approach, and it meets these nice criteria. It's open source, so it's ready for those of you here in academia to contribute if you like, develop new fancy testers, new type systems, new policy languages. We'd love to collaborate with you. So thank you.
Really interesting talk, thank you. I was curious about your first name, that Cedar is ergonomic. So I see, it looks ergonomic to me. You make a good argument. I'm wondering, have you looked at anything empirical, either qualitative or quantitative on this?
Right, great question. So empirical studies are more convincing than just hand-wavy claims in terms of usability. So we do have some internal case studies at AWS. They haven't been published yet. There's a whole sort of usability group that will do studies on your behalf with developers, and so we did play test the syntax with them. We have informal anecdotal feedback from customers that they prefer the Cedar syntax. That is only anecdotal, it's not through a study. It would be great to do some sort of study. I don't know the prospects for that in terms of our team being able to do it. We'll see whether we can make that a priority. But I think evidence is always better than not evidence.
Thanks again. I was curious about some of the automated testing capabilities. You mentioned that you have this input generation system for doing differential testing of the implementation and the formal model. So I'm curious from the customer's point of view, have you seen them wanting to use any sort of input generation for debugging or testing the policies that they write? Or anecdotally, what is their process for identifying, have I written the right policy beyond just like the basic, deny all versus allow all?
Right. So the question is, could input generation be used by users as well, and not just for our own testing? That is a good question. Users definitely do write their own unit tests. I have not personally seen a request to generate inputs using tools. Users tend to want to write their own inputs, I guess. I have a sort of an idea that's on the back burner that I proposed before of using a sort of symbolic execution of a policy. Basically, you could look at a Cedar policy and enumerate all of the paths through the policy and pretty easily generate a minimal set of tests that would capture every path in the policy. And you could suggest that to users as a set of tests that they might confirm for themselves that they're getting the answers that they wanted. When I bring this up to people, they like the idea of it, but somehow it hasn't been raised to a high enough priority. So I think it's a good idea, but it's just not happening.
And just follow up, anecdotally, have you seen any instances where users had to debug their policies and found bugs, and what are some of the pain points in writing Cedar policy?
Yes, people do debug policies or have made mistakes in writing their policies. I would say the main one is not understanding negation. Intending, for example, to do forbid not and thinking that that's going to be permit, rather than maybe it's related to a misunderstanding. Actually, I guess it isn't, to what Carl was saying. Instead of thinking of it as, well, permit is a bunch of positive permissions and forbid eliminates them, they feel like if you do a forbid with an unless, then that's actually permitting something. It's like permitting the negation of the forbid policy, so people get confused about that. I'll see if I can think of other examples for when we talk later.
Sure, thanks.
Carl?
So I'm a little curious about the verification you did of the reference implementation. So the reference implementation isn't the running code, so you did some sort of testing thing to compare it with that. So what's the spec for the reference implementation? It seems like, once you've written some idealized code, the spec could be almost the same as the code, or is it just not that idealized?
So no, you have it exactly right. The reference implementation is the spec. That's the way we view it.
Okay, so what were you proving about the reference implementation?
The reference implementation, that it has certain properties that you would like the reference implementation to have, so that it's default deny, that forbid always does override permit, that the validator is sound. The functional specification is the implementation itself.
My other question, some other hands. So you're familiar with the proof carrying authorization. So I imagine that it's, just not remotely fast enough for your purposes. But one of the things that that could do is it has this idea of delegation, where you just say, you could do something if so-and-so says so. Can you do anything like that here?
There's no notion of delegation built into Cedar. That is something that we've had in mind. So at the moment, Cedar was built for this for supporting this Amazon verified permissions centralized AWS service. What we find is that a lot of customers want basically centralized authorization, so they can go to one place and look at it. But other customers absolutely do want federated authorization, where you have the reason you're allowed to do it is because this other trusted party says you're allowed to do it. So I think you could extend Cedar to support notions of delegation. We have these notions of entity and hierarchy there already. I think you could extend those to support proof carrying authorization, but not in the current.
So you made a really interesting claim at the end, which is that lean is less brittle than Daphne, and I didn't see any particular reason to think that that's the case. So I'm wondering, why did you think it would be the case, or why do you think it was successful when you did the small refactoring for the library?
Good question. So I should have said that before. The reason is, sorry, thanks, Virgil, I'll call you in a sec. The reason is that basically the automation that's embodied in the tactics in lean is just a lot more scoped in scale so that it's more predictable. Whereas the automation that Daphne is using, which is compiling verifications conditions down to SMT, there's just so many more heuristics and fanciness that's there that it becomes much harder to predict what's going to happen. So that's why we expected the proof effort to be more significant for lean. There's more kind of by design on the user. But we felt like the maintainability benefits were worth it. Go ahead, Virgil.
Okay, wonderful talk. Thank you. I'd like to ask you a couple of very quick questions, and the yes or no answers would be good. So one is, suppose that I turn on my system, and the question that I have, is it in a secure state? Namely, does it satisfy any of the specified policies? Can you actually handle that type of questions in Cedar?
You can, to the extent that you can specify what secure state means in Cedar policies, which is probably not all that you might like.
So if you're talking about the policy, any proof of the policy requires the policy to commands to start in some sort of an initial state that satisfies the policy. So the question is, can you actually specify initial secure states in Cedar? And if so, can you check them when I turn on my system?
Right, so what you would do is you would write policies that define your initial secure state, and then when you turned on your system would have to pass along its footprint over to the authorization engine, which could then check whether or not all of those policies were satisfied.
Mm-hmm. Okay, so quickly, how about you specified all sorts of very useful policies, role-based, attribute-based, and so on. Can you specify a variety of separation of duty policies based on those? And if so, have you so far?
So Cedar is an authorization language, so it's about what you are allowed to do as opposed to what you should or shouldn't be allowed to do in terms of constraints, right? So I think of separation of duty as something like, if you're permitted to do this, you should be permitted to do that, or if you're permitted to do that, you shouldn't be permitted to do this, something like that. You probably
that's one of them, but there are maybe a dozen specified so far.
So with that as an example, you could write that as sort of a forbid policy. You could write permits and as forbid describe the circumstances under which authorization should not be allowed because of a conflict of separation of duty. I would think that would be the most direct way. But you could also use policy analysis to write arbitrary queries looking for invariants that express your separation of duty constraints and prove that your policy store satisfies those.
Right. So last quick question. So Cedar allows you to specify these global policies for your Amazon applications. Now, suppose that I import an application from Microsoft or from Splunk or from Google or for somebody that has its own internal policy. How do I make them work together? How do I know that your subsystem, which is based on Cedar, would not inadvertently deny accesses that my application that I imported runs?
So Cedar is general purpose. It's not just for AWS. It's however you want to map its notion of action or data entity to your particular application's abstractions. But it does require you to perform that mapping stage. So if I were to hypothetically import some existing application and want it to use Cedar, I'd have to modify that application to start delegating requests to Cedar. And then it would be up to the author of the application to figure out how to make any existing logic, if they wanted to keep it, work with the new logic they would implement in Cedar.
So if I understand you correctly, you have to modify the application, not just modify the Cedar specifications.
Yes.
Okay. Thank you.
Thank you.
So I think in the interest of time, let's thank Mike again. Thanks, everyone.